Today we're talking about lesson 1-3, which is exploring real numbers. In algebra, we're going to be talking about real numbers the whole year. So you'll kind of see that within everything we work with, it's basically a real number. And when we find things that aren't real numbers as solutions, we're just going to be basically ignoring them for this year. And then eventually what you'll find is that you'll actually have different symbols and different things that you can do with those other numbers. But this year our focus is really within real numbers. What I want you to do after we take notes today is go to your book and go to page 18. Or you can open your book to page 18 right now while we're taking our notes. There is a chart on page 18 that is really great to just look at as we go through this, because it shows you how all the numbers are relating to each other. And again, we're only talking about the real numbers. So, real numbers, we have natural numbers, those are part of the real numbers. And natural numbers are 1, 2, 3, just goes on counting. Whole numbers are all of the natural numbers, but we're also including 0. 0, 1, 2, 3, and counting up from there. So you just need to memorize the difference between whole and natural there. Integers, again, these are all real numbers. Every one of these falls under the big category of real numbers. And within real numbers we have whole numbers, which are 0 and up. We have natural numbers, which are 1 and up. We have integers. Integers are all of the natural and whole numbers, but also including all of the negative. So everything, and then -2, -1, 0, 1, 2, and then everything from there. All of our counting numbers with negatives included. Okay, all of these are called rational numbers, and again, they're under real numbers. So what you want to think about when you're thinking about how to categorize these, because it used to confuse me when I was thinking, well, wait a minute, but one's in this category, in this category, in this category, and in this category, and it's a real number. So what you want to stop and think about is just use it in an example that you know about life. So there's animals, and within animals you have different categories of animals you might look at. So there's an animal that lives in the ocean. Well, there's a lot of them. Okay, so maybe animals are real numbers. And there's a lot of animals that live in the ocean, so maybe those are our natural. But then there's animals that live in the ocean and on land, and those are our integers. So they're still under that big category. And you can kind of simplify down to where maybe you end up with something that is a specific type of animal that lives in the ocean. Still under an animal, but it just gets broken down into further categories. So that's kind of a way to look at all of this, and that's what this chart will really help you with. So rational numbers are any number that you can write in the form A over B. And A and B are just any numbers where A and B are integers. So integers here. But there's one thing you need to know, and that's that B cannot equal 0. This means cannot equal. And again, the reason B cannot equal 0 is from what you've already learned. you cannot have 0 in the denominator of a fraction there. A can be 0, but B can't. So an example of a rational number would be something like 2 over 4. Or it could even be something like this, 54 divided by 18. And when you stop and think about that, that actually simplifies to be 3, which ends up being an integer or a whole number or a natural number. So these all fall under rational numbers because they can all be represented as a rational number. Even if I just took something like 2 and put it over 1, I end up with 2. When you have rational numbers in decimal form, it's going to be a decimal that either terminates, which means ends, or repeats. So you're going to end up with an ending or a repeating decimal. For example, when I divided something here, I might end up with something like 6.27. So that's terminating, it ended. Or I might end up with something like 8.22, and I realize it's continuing, and it's going to repeat. So these fall under rational numbers. If we were to look at what we have so far, all rational numbers can fit into the category of natural numbers, whole numbers, or integers, depending on what that is. So integers are a rational number, whole numbers are a rational number, and natural numbers are a rational number. These 3 types of numbers all fit under rational numbers, and rational numbers fit under real numbers. The next type of number that fits under real numbers is called irrational. So you don't see as many of these because, remember, these 3 all fit under rational numbers. So irrational numbers are the type that you're not going to come across as often this year, but you will see them. And an irrational number cannot be expressed in the A over B form, where A and B are integers. And the way that you can tell easily if it's an irrational number is by converting it to decimal form. And when it's in decimal form, the decimal never ends. It's never going to end. And we're not talking about repeating. And doesn't repeat. So in order for you to actually tell if something's an irrational number, you need to put it in decimal form. And on the homework, you're just going to use your calculator if you need to convert some of the things that you're given. And you'll look and just tell when you convert it to a decimal, if it ends or repeats, you're going to call it rational. And if it's irrational, it won't end. And typically the way that you can tell that is when you put it into the calculator, it goes to the end as far as you can go, and you don't notice a repeating pattern by then. That's the easiest way for you to figure that out. So an example of that would be something like pi. Okay, you've all talked about pi, and most of us have memorized it as 3.14, but there's a lot more behind that that just keeps going, and it doesn't repeat. Another example of that is if you were to put the square root of 10 into your calculator, and just in case you're not sure of how to do that, most calculators are going to have something that looks like this. Let's see if we can get it. And that's your square root symbol right there. So you would type in 10. Some calculators you need to type the square root first. Some calculators you type it second. So in this one, I take 10 and the square root. Notice it's going off the end, so it's not going to repeat and it's not ending. It's irrational. So let's try a few examples of classifying these numbers. If I was to give you the number 23, go back and look at what we just took notes on and write down everything that it would fall under, because it's going to fall under more than just one of those things. So hit pause, write them down, and then come back. And now that you're back, we can look at these. So 23 is obviously a real number, because we've already talked about that. So we know it's a real number. And then you want to look from there, is it rational or is it irrational? That's the way I break these down. So I start, it's a real number. And then from there I say, okay, is it rational, is it irrational? It's rational because it can be represented just like the definition we talked about. So it falls under rational number. Now that it falls under rational, if it fell under irrational, you'd be done at this point because we didn't have any subcategories under irrational. But now that we have rational, you need to stop and look. Is it an integer? 23 is an integer, so it's an integer. Is it a whole number? And it is a whole number. And it's also a natural number, because remember, the only difference between whole numbers and natural numbers is having 0. So let's try this again. Look at another one. Let's try 0. So again, hit pause, write down what you think it falls under, and then come back. So we know it's a real number. And now again you determine, is it rational or is it irrational? And it's actually rational because this would be a. So if you think about it as a fraction, it would be 0 over 1. And remember, we can have a can be 0, it's just b that can't be 0. Now you need to take a little bit of a closer look at, is it an integer? Yes. And it's a whole number because it has 0. It's not natural because there's no 0 included there. So here's another example. Do the same thing, just hit pause after I write it down and then check it after. 4.581. So this is a real number. And now within real numbers we want to look, is it rational or is it irrational? It ends, it's a decimal that ends. So this would be rational. Now from here we look to think about, is it an integer, a whole number, or a natural number? Because we have numbers after the decimal and not 0 after the decimal, we're done here. It's not going to be natural, it's not going to be whole, and it's not going to be an integer. Because remember, our natural, our whole, and our integers are basically like our counting numbers, and then the integers are the negatives included. So you're done here. We'll have a chance to look at more of these tomorrow, and you can ask further questions about them as you go through it. So throughout the year, you're going to hear me use the word give a counterexample, and you're going to see that in your book. So a counterexample is just proving something different through an example. Like if I was to say all whole numbers are natural numbers. And then I had to decide if that's true or false. Are all whole numbers natural numbers? And then you would prove that right or wrong based on a counter example. So when you stop and think about that, natural numbers include 1, 2, 3, 4, and so on. Whole numbers include 0, and 0 is not included in these natural numbers. So the word all makes this false, and this is false because 0 is a whole number, but it is not a natural number. So that's how you use counterexamples. Really important to be able to at least think through questions like this by finding counterexamples throughout the year. But sometimes I'll actually ask you to come up with one if you're saying it's false, and other times you'll just use that idea to help you break it down. For the next few examples, I'm actually going to go through these very, very quickly because I feel like most of you probably already know what to do, but it has been a long summer, so I'm just going to go ahead and give a quick review. First thing we're going to talk about is ordering fractions. Okay, you have two options for ordering fractions. So you can either convert all fractions to decimals, which is what I usually prefer to do unless it's really, really easy to use the second way, which is or find a common denominator, a least common denominator. So either or, I think you all know how to find common denominators. If you don't, please ask me tomorrow. And I think you all know how to convert to decimals. The biggest thing that you need to be aware of is watch negatives. Because remember, negatives kind of go the opposite. So the larger the number, the further away it is, the smaller it is. So just be careful with that as you're thinking about your negatives. So let's just do one example of this and then we're just going to move on. And if you have trouble with it, please let me know. Order -3/8, -1/2, and -5/12. And it's from least to greatest. So in case you forgot how to convert these to decimals, denominator divides into numerator. And I'm just going to go ahead and give you these answers right now just so we can walk through it pretty quickly. So -3/8 is equal to a -0.375. Obviously -1/2 is equal to a -0.5. And then -5/12 is equal to -0.416, and 6 is repeating. So because all of your numbers are negative, remember least to greatest actually is going to mean that you need to think about the larger the number with the negatives is actually going to be a smaller number. So the easiest way to do that for me is to go through now and think about, this is the furthest back, so this is going to be the smallest number, then the 4, and then the 3. And now I can go write my answer in that order. So -1/2. And then the second one was -5/12, and then the third -3/8. So you just have to think opposite when you're talking about negatives. And then the last example is talking about the difference between opposite and absolute value. So opposites are positive versus negative. So an example of that would be -2 and 2. Those are opposites. Absolute value is distance from 0. Distance can't be negative. So the difference here is that absolute value is just always positive. Absolute value of 2 equals 2, where the opposite of 2 would be -2. And the absolute value of -2 is 2. So always positive. Now a quick example where I see mistakes sometimes that you want to just be aware of. If I have something like 7 minus 2 and that's in the absolute value, you treat this like parentheses. You simplify, then take absolute value. So it is not going to be the absolute value of 7 plus 2. I see a lot of students try to do that. It's not that. You actually simplify, so I get absolute value of 5, and then I end up with 5, and that's my final answer. So always simplify within there first, then take a positive final answer. So that is lesson 1-3, and we will go over more of this tomorrow.